So the idea for today is to start talking about, or spend, hopefully get through much of talking about making your code run more quickly in R. So basically different means of writing more efficient code. So I'll start by just showing a couple of the tools for actually assessing how fast a piece of code will run and trying to see what are the bottlenecks in your code are. So the first thing is there's just a simple function called system.time that will show how long it took to run a particular chunk of code. So I'm just going to illustrate here by contrasting the time it would take from, I've just made a matrix here, and I'm going to do system time where I use a for loop to go through and find the row mean, the mean of each of the rows, and then I'm going to contrast that with using this built-in function called row means, which is actually very, very, very fast. So if we do that, what you'll see is it reports the time in fractions of a second. In general, we want to pay attention to the elapsed time. That's basically the clock time that it took to run. And you can see that, for example, doing the for loop took about 10 times an order of magnitude longer than using row means for this particular case. And it's going to vary depending on exactly how many rows there are and how many columns there are and things like that. But that's the sort of result that you'll often get when you do a comparison like this. There is some stochasticity if I had actually run that same thing just before I started class, just to make sure things were running reasonably in our studio, and I was getting the timing was showing up in the way I expected it to. You can see when I ran it previously, it was, there was some kind of difference in the amount of time each of these pieces took, depending on the fact that I ran it again. So there's some stochasticity here that depends on what else is going on your machine at any given time. And it can also matter whether you run the same code multiple times in a row, because sometimes there's caching of certain intermediate variables and things like this. It all depends on sort of how the hardware is set up. So that's good motivation for using this nice tool called benchmark. So this is a function in the R benchmark package. And what it will do is it will replicate any given expression that you want it to, and it'll also compare across multiple expressions. So a sort of standard thing to do would be to do something like this. So here I'm just going to say benchmark for this single expression, do it 10 times and report back these particular possible fields in terms of the results of the benchmarking. So those are sort of the standard ones that we might report back. And if I do that, it'll go through and it'll say, okay, you asked for 10 replications. I did 10 replications of this particular chunk of this particular call to code, and it took this long, so almost a second to do those 10 replications. In general, it's often going to be more interesting to actually compare multiple pieces of code, so I'll just do the same thing that we did before with system time, but here I'll do it with row means. I'll do it with row means and I'll do it with for loop, but within the benchmark, called to the benchmark function. So if I do that, it will show me the it will show me what was the code that I ran. That's in this test column. How long did it take? How many replications? Again, we see it's about 10 orders of magnitude. We have a little more confidence in this because this is averaging over 10 replications. So we've averaged over some of the stochasticity there. Okay, any questions about either of those? Okay. So if you have some idea of what the pieces of code or what the operations are that you want to contrast, those are quite helpful. But sometimes often you're going to be running some big workflow or pipeline, and you've got many, many steps in your code, and you want to be able to get some sense of where the bottlenecks are, because there's not a lot of point in spending a lot of time trying to optimize one of your lines of code if that line of code only takes up 1% of the processing, and the rest of it takes up, there's some other piece in there that takes up 90%. So that's where this functionality for profiling comes in handy. So I'm going to show you, just give you a quick demo of that. So this function is a function that will basically create a random time series. So what it does is it just makes a grid of time points. So that's what this first line does. So I'm just going to, because I can't do this infinitely fine gradation, I'm going to do this on a grid of points. So you can think of this as a grid of time points. And then I'm going to find out what are all the pairwise distances between each of those time points. That's what this rdist function is going to do. So that's going to create a matrix that is len by len, because that's the number of time points I have. And then I'm going to create a correlation matrix based on that set of distances and based on a parameter. So this is just an exponential correlation. The correlation decays exponentially depending on the lag between any pair of time points. So this is basically going to allow me to generate from a Gaussian process with an exponential correlation function. So some of you may have run across Gaussian processes which are a particular kind of stochastic process, and that's what I'm generating from here. So this is going to generate a correlation matrix, a len by len correlation matrix. And then we'll see this in the linear algebra unit in a number of weeks. I'm going to take the Cholesky decomposition of that, so that's a matrix decomposition. And if I take this particular matrix decomposition, multiply the resulting, this is basically a square root matrix, multiply that matrix by a vector of random normal standard 0, 1s. I will then generate from a Gaussian process with the correlation matrix specified by this C matrix. So this is generating the square root matrix. This is just generating a vector of standard normals. And then when I do cross prod of U and white, that generates my Gaussian process. So this is basically a standard algorithm for generating from a Gaussian process. And it's more or less the most efficient thing that you can do. And we can go ahead and see where the bottlenecks are in doing these calculations using this profiling. So I'm just going to create the function. I need the fields package because that's what the rdist function is in. And then I'm going to make two calls to this rprof function. I'm going to just initialize it, then I'm going to run my code, and then I'm going to sort of finish it off and tell it to sort of wrap things up and do some cleaning up. And then I'm going to use this summary rprof on that file that I created when I did the initialization, and that's going to print out the information about the profiling. Okay, so any questions about what the goal here is, or what it is that I'm doing? Okay, so if I do this, what it's going to do is print out a bunch of information in the form of two tables that are called by self and by total. If you look at the PDF, you'll see the results are somewhat different, which may have something to do with running this code on my laptop versus running it on a Linux machine on the SCF. But what it'll basically show you is the by total. So any function calls, many of these function calls are then going to call subsequent functions. And so the by total says, if I call a function, what's the total amount of time taken in that function, any functions that are called from within that function. And the by self tries to isolate the timing to what happened in any particular function and not in functions that were called by that function. So it's trying to sort of piece apart what's happening, where sort of the guts of the processing are going on. So if we look at the by self, it looks like what's going on, and this should add up to 100%. It looks like most of the time is spent in chal.default. So if you remember, when one of the lines of code up here was to do this matrix decomposition of this Cholesky decomposition, and so this is indicating to us that this is the call that's actually taking the large majority of the time. That it's in the calculation of this matrix decomposition. The reason it's chal.default and not chal is an S3 generic method, which we'll talk about in a couple days. And so when I call chal, it ends up then very quickly just calling chal.default, and that's where the bulk of the actual decomposition occurs. So that tells us that that's sort of the bulk, in this particular calculation, the bulk of the computations. That's not surprising to me, and it may not be surprising to some of you, because matrix decompositions are generally quite expensive and are often order of n cubed, where n is the size of the matrix. So in this case, we had 1,000 by 1,000 matrix. It's going to scale as 1,000 to the third power. So it also says there's a bunch of time spent in doing a minus, a bunch of time spent in doing a call to some Fortran code. I'm not sure what that assign is going on. That's interesting. There's some time spent in exponentiation. So a little bit of that is not directly obvious from doing this here because we don't actually see any minuses in here, and we don't see any .fortran calls in here. So if we really want to sort of get to the bottom of what's going on, we need to sort of drill down into some of the particular function calls. It helps a little bit. We could look at the by total, and that'll help give us a little bit of sense of what's going on to help interpret what we saw in the by self. So remember, in the by self, we saw there was a lot of time in chal.default. In the by total, we can see that, oh, what probably happened was most of the time is spent in chal, but then it's just calling chal.default quite quickly. And so 70% of the time is spent in the chal.default, like we saw up here. A little bit of the time is spent in chal as it's doing the pass along and pass through to the chal.default. The standard generic is also part of the dispatching, where it goes from us initially just calling chal to it then calling this default method for bringing it to us in composition. So it then tells us that, oh, okay, about 12% of the time was spent in doing this rdist, which is calculating this matrix of all pairwise distances between my gridded discrete time points. And presumably, the minus is in rdist, both because if we think about what a distance function is, it's going to involve doing a subtraction, and because if we look through this some more, we would see that basically what happens in rdist is it does a minus, and there's a call to .fortran, and these are basically adding up to this, I believe. Although actually the matrix is also in there. So sometimes it gets a little bit confusing in sort of exactly how things are being parsed apart. But in general, you can get a pretty good sense for where the bulk of the computations is. If we actually looked at that rdist function, that would help us in teasing things apart a little bit more. So we can see in rdist that there's some pre-processing about checking whether things are matrices, are things missing, et cetera, getting dimensions of the matrix. And then we can see it does a call to some Fortran code. That's what this .fortran does. So calculating distances would be something that would be very slow if you just did it in R code, and so it's going to be much faster. And the package developers wrote the code such that they basically pass the data off to a Fortran function. Stuff gets done very quickly in the Fortran function, and then stuff gets returned back to R. And so this is where some chunk of the processing is getting done. And this might be that matrix call that was mentioned in the R profiling as well. Let me go back up and see if there's anything else to mention here. I don't think I want to belabor this too much more, but hopefully you've gotten sort of a general sense of how to interpret this and how you might start to drill down and see where these different function calls are being made. Are there any questions about what I've just gone over here? Yeah.
Is there a way to break that even more? For instance, if we have a lot of time spent in the Fortran call, can we break down what's happening in Fortran?
That's probably going to be tricky because that sort of ends up being sort of a black box to us. And unless you really want to dig down deep and start changing the Fortran code yourself, which is somewhat unlikely, it might not help you that much to know where the time is spent in the Fortran function. You might, I think, oftentimes you're probably just going to treat that as a black box. And if it's sort of this, unless that Fortran code were really written inefficiently, the hope is that the people writing that code knew what they were doing, and that's basically more or less as efficient as it's going to get. Other questions?
Is there a way to rate just comment timeline line by line?
That's a good question. Yeah, because this does make it a little bit more opaque in terms of where things are. Yeah, so it would be nice to just see it line by line. I don't know of any function that will do that, but yeah, that's certainly a good question. Anything else? Okay, so those are some tools that allow us to basically assess how fast some code is going to run. Now let's go through and just work through some of the basic strategies that people who work with R will generally tend to use to make sure that their code is running reasonably efficiently. So one thing that is important to recognize is that in general, it's pretty inefficient to create a small object and then keep sequentially making it bigger and bigger by tacking pieces onto the end of that object. And that's true whether you're doing a concatenate with the C function and just concatenating onto a vector, or a C bind or an R bind and concatenating onto a matrix, or if you're doing a list and you're concatenating elements onto a smaller list. So here's an example of that where I'm going to do a benchmark of, and this is a silly example because all I'm doing here is just creating a vector 1, 2, 3, so on and so forth. Obviously we would just do that with 1 colon, however long I want to make the vector. But this is just to illustrate that if we were to make that vector by sequentially piecing stuff on it, that's much slower than if we create the entire vector and fill it with missing values and then sequentially fill the entries of that vector. So I'm going to contrast doing a for loop where I initialize x to just be 1 and then I concatenate x with I. So this is just going to keep growing the vector one piece at a time, versus making the vector all to start with using rep and then a, and then filling the vector with a for loop, and x of I gets I. So neither of these are going to be very efficient, and we would never actually want to write this code because there's no reason to write for loops in this case. But this just illustrates that, that this is going to be in particular quite slow. So if we do that, we can see that the case where we're tacking things on at the end is about 10 times slower than the case where we make the vector and then fill in to that vector. So basically the reason for this disparity in speed is that if we start tacking things on, what actually is happening under the hood in terms of R is first it makes that initial x that has the value 1. And then when it goes to tack on the next value to that scalar, to that one long vector, it has to make a new vector that's 2 long. And then when it tacks on the third piece, it has to make a new vector that's 3 long. So every time you tack something on, you're making a new vector, and what R has to do is go ask the operating system for the memory to allocate to make that new vector. And once you get up to making longer and longer vectors and having to do that many times, you're having to make n different memory allocations to request space from the operating system. Whereas what happens under the hood when you do this, where you create the vector initially and then you fill it in, is you ask the operating system once for that vector, and then it turns out that R doesn't need to make a copy when it fills in the individual pieces of that vector. It's just able to put the piece in the already allocated space in memory. So that's useful to know. And there is an even faster way to do it. You can actually exploit in the fact that that you can sort of just manipulate the length of a vector. You can actually say, let me just get a single scalar, a vector of length 1, and then change the attribute, the length of that vector, to be n. I don't know exactly why this is faster, but that's actually slightly faster than allocating the full vector using rep. This is sort of a minor, somewhat of a side point. Same thing happens if you can do similar sorts of things with matrices. You could create a single single scalar and then tell it to be of dimension number of columns by number of rows, and that will allocate that matrix quite quickly. And if you want to allocate a list as opposed to tacking on elements of a list one by one, the idea is you would first create a list of a certain length. Recall that a list is just an R vector, and so we can use it with a call to this function vector. So that's sort of the basic story, just that you don't want to create objects and keep tacking, making them longer and longer by tacking stuff on. Any questions about that? Okay, so the next major principle is to do calculations in a vectorized fashion. You guys already are at least somewhat familiar with this. So here I'm going to I guess it looks like I'm using system.time here. I thought I'd change things over to use benchmark for most cases. But what I'm going to do is I'm going to just square a fairly long vector. So I'm going to create a vector that's a million long and or 100,000 long, and I'm going to square it in using a vectorized calculation where I just make x2 be the square of the vector x. If I do that, that goes pretty quickly. On the other hand, if I use a for loop and sequentially square each element of the vector, I'm going to have to wait a little bit. And this is the contrast in time. 3 seconds versus 3,000ths of a second. Right? So this is a pretty big difference. Right? There's 3 orders of magnitude. And so if you were writing R code that uses a lot of vectors, that uses a lot of for loops in that fashion, you are going to slow down your code quite substantially. And I forget if I've said this, but oftentimes people, when they're thinking about comparing R to other languages, will say, "Oh, R is really slow and it's interpreted and all this." And that's by and large somewhat true. But I think it's also a function of the fact that sometimes when people do these comparisons across languages, they may try and write the code in the same way in every language. So they might use a for loop in R and compare that to some, let's say, MATLAB or C or something like that, as opposed to writing code in the way that is the best way to write it in the particular language. And so you can get pretty good performance in R by recognizing some of these various principles that we're going over. Okay, as I've mentioned before, lots and lots of functions are already vectorized. So even things like string functions, as we've been seeing, will operate on a vector of character strings and do the same thing to each string within that vector. So substring operates in that way. Grep, gsub, all of the functions that you're using on the problem set will all operate in a vectorized fashion.
Question.
Yes.
So does R do any parallel processing in the hood?
It is, yeah, we're going to talk about that in some detail. Basically, it will, if you have the right underlying linear algebra packages installed, it will do linear algebra in parallel. In general, unless you explicitly tell it to, it's not going to do other kinds of operations in parallel, unlike something like MATLAB, where it has some of the calculations be threaded sort of natively. But there is a fair amount of parallel processing functionality that you can use with add-on packages in R, and we'll cover that in a few weeks. Other questions?
So the speed difference is not really because R has the stuff into parallel processing functions.
Oh, right. No, that's right. I'm glad you brought that up because I was gonna say something about why these two are so different. So if we think about what's happening under the hood here, basically what's happening here is R is basically taking that whole vector x, passing it to a C function, basically running the compiled code. The C code has been compiled. It's running that code quite quickly, as quickly as if you had written that C code yourself. In fact, probably more quickly than if you'd written that C code yourself, because you probably wouldn't have written the C code as efficiently as the developers of R did. Whereas what's happening here is R is basically stepping through this for loop line by line and having to interpret the code. So instead of running the for loop in C, which is what's happening here, and there is a for loop going on when you do this, except that the for loop is running in C, and the code has been compiled. Here, the for loop is running natively in R, and it's basically having to step through each of these, each of the lines. It's setting I equals 1, then it's going in and changing, doing this for I equals 1, then it's setting I equals 2, then this for I equals 2. Stepping through that, because R is an interpreted language rather than a compiled language, stepping through all that, there's a lot of overhead involved. So, and this is a particularly egregious case of it because most of this calculation, when you do it natively in R, most of the time is spent in doing the overhead as opposed to doing the actual calculation, because squaring a number is pretty fast. So most of the time spent in doing this, if you do it in R, is spent on doing sort of the overhead of managing the iterations and whatnot. And that's why this is a case where it's particularly faster to do it in a vectorized way. Just want to mention that there are oftentimes pretty clever ways to do things more quickly, and sometimes this won't matter. Sometimes it's not going to be worth your time to sort of figure out how to do this in a more efficient, but in a way where the code is maybe a bit less clear. So here's an example of taking all of the values in a vector that's of a vector called x, and anything bigger than 0 setting it to 0. So I'm just doing some truncation. So again, it's a fairly long vector. It's a million long, and if I use the if-else function, I'm going to compare that with using just subsetting in with the square brackets and using vectorized comparisons and working with Booleans. Versus, here's my third one. That's sort of a clever way to do it, but maybe not something that is immediately clear what's going on when you just look at the code, which is I'm taking, think about what's going on here. Well, what's the result of doing x bigger than 0? What do I get? I get a vector of, actually I get trues and falses initially, right? And then if I take a vector of trues and falses and try and multiply them by a number, the trues falses get coerced into zeros and ones get multiplied by the original vector, and anything that was a false or a zero gets, basically zeroes out the element of x. So I guess when I originally introduced this, I said the truncation wrong. I'm truncating everything that's less than 0 to be 0. So this does things basically by doing math operations. This does things by sort of doing some subsetting, and that does things by using this if-else function. Oftentimes, if you can reduce it down to doing sort of mathematical calculations on Booleans and numbers, then that's actually often going to be the fastest thing. But in your particular context, it may not matter that much. Looks like this is taking a little while to run. So it's sort of interesting here. You'd think that if-else as a sort of a basic built-in R function might be fairly quick. Turns out if-else is actually quite slow. It's something like an order of magnitude slower than if I used the subsetting here. And it's actually, this is even 3 or 4 times faster by doing it, just in terms of mathematical operations. So the sort of thing, so this sort of points out, we might, if we had done some profiling, and if we had if-else and that was where a lot of the time was being spent, we might have found out by doing the profiling that if-else was where a lot of the time was being spent. And that might have led us to thinking about, well, is there some other way I could do this truncation that might not involve if-else? And it might lead us to thinking a little bit about, why does if-else seem so slow compared to these other ways of doing this? So the usual way to address that is just to try and look at the code and get a sense for what's going on. And oftentimes when we're doing this, we're often going to expect that if it's a built-in R function, that it's actually going to do a little bit of pre-processing, and then it's going to go call a Fortran function or a C function. And if it does do that, what you would see is you will see either .call or .c or .fortran, or you'll see a call to some function called internal or primitive. All of those things indicate that it's going off and calling some compiled code. On the other hand, if we look at if-else, we see that there's actually none of those kinds of calls, which is a little bit surprising. But it looks like if-else is built all in native R code. And so it's doing some testing, and it's doing something with NAs, and then it's doing something with replication, but you can see there's no call to any compiled code. So presumably the reason that this is fairly slow is it's all just using R, sort of native R calculations. Whereas the subsetting and the comparison operators and whatnot, that would actually do a call to some compiled code. So if we were to, for example, look at, I think this will work, look at what the greater than, so this, at the core of a couple of those other ways of doing these calculations, there was using the greater than or less than symbol. Right? So this was doing vectorized comparisons. And if we look to see how does R actually carry out comparisons, well, any operator is just a function. We can look at the code that gets run when we run that operator by putting the operator in backticks. And what it says is, well, the greater than sign is a function. It takes 2 arguments, the thing on the left side and the thing on the right side. And then it does a call to primitive of the greater than. So it's just basically calling some compiled C code under the hood. And it's basically doing that directly. There's no, this is just a straight pass-through to the underlying compiled code. So that's the reason essentially that's going to run quite quickly. Okay, any questions or comments about that? Just remind myself of where I am here. Oh, just a comment here. This was a problem that I had folks work on during the boot camp, so I won't ask you guys to do it here because a number of you have already seen this. But if you haven't seen this, and it's not immediately obvious to you how to do this, this is a worthwhile problem to try out. This is a chi-square statistic calculation. You get a contingency table, a 2x2 table, and you're calculating the difference between the observed values in the table and the expected values under an assumption of independence. You should be able to do this calculation with 2 lines of R code that don't use any for loops. So if that sounds like something that's not obvious to you right now, that would be a worthwhile little problem to try out. Okay, let me make a couple more comments about working with matrices. So I forget if I think we've talked about this briefly before, this idea that R stores a matrix basically as a flattened vector where it's stored by columns. So the first element of the vector is the 1, 1 element of the matrix. The second element of the vector is the second row, first column of the matrix. So if we think of a matrix, basically it's stored as a vector, kind of like this. And so you can think of what's going on under the hood as R is basically storing that as a big long vector. Starts at some location in memory. The first column is stored as the first piece, the second column is the second piece, the third column is the third piece, so it's contiguous in memory like that. So if you're thinking about in what order to do calculations, do I do things over the rows or do I do things over the columns? One thing that's useful to think about is how is R, and sort of the computer more generally, how is it going to access the information? If I'm, for example, trying to calculate the mean of a row, what needs to happen when the computer needs to go get the pieces of information to do that calculation? So to get a row, if I want to do the mean of this row, I need to get this one, I need to get this one, I need to get this one, etc. So what's going to happen? The computer's going to have to go get this, and then it's going to have to jump along a ways and come here and get this, and then it's going to have to jump along a ways and get this, and it's going to have to collect those pieces and then take the mean of them. That's going to be slow because it's going to be faster for the machine to get this first piece and then just increment by a little bit and get the second piece. So in general, it's going to be faster to calculate the mean of a column than it is to calculate the mean of the row because of the way that the information is laid out in the machine's memory. So that suggests a few things. One is that if you're concerned about efficiency, and oftentimes it's not going to make a difference if you're working with fairly small matrices, but sometimes it might be worth thinking about this, is that if I have a choice of filling up my matrix by row or by column, and then if I have to do a for loop, for example, doing a for loop or doing a row means or an apply or something like that, doing it by row or doing it by column or doing it by row, if I can do it by column and operate on individual columns, it's probably going to be somewhat faster than doing it by row and operating by individual rows, because whenever I do an operation by columns, I can just go in, do something to the column, and all the pieces are right there sitting next to each other in memory. That sort of also ties in with this point about doing basically sort of direct mathematical operations on matrices and vectors, which is if you have, say, a matrix A and you have a vector B and you do this operation, suppose this is our matrix A, and I've got I have a vector B. What's going to happen is this is not going to do a matrix multiplication. This is going to do a multiplication of this vector by this column and give me a new column, this vector by the second column and give me a new column, and so it's going to create something that's also a matrix where this first one is the first one times that, and the second one is the second one times this, etc., etc. So it sort of makes sense that this is how R interprets this, because this is naturally is an operation that's based on having stuff stored by column. There's not a way for me to take this vector B, assuming that it's of the right length, and multiply it by each of the rows. Okay? So the reason it's set up and the reason it does it this way is because R is storing things in this column major order. What if I did want to do this vector times each of the rows of A? What could I do to get around that? Okay, I could just take the transpose of the matrix A, assuming that the matrix A has the right dimensions to be able to match up with the length of B. I could do transpose of A times B. And then presumably I want to do another transpose to get things back in the order that I had them in originally. So now I'm going to wrap that in another transpose. So even though there's some time involved in doing the transposing, it's possible that this is going to be faster than, say, writing a for loop or doing doing this in some other fashion. Okay, and then sort of a last comment about this, which is that, you know, if you're used to programming in R, this looks pretty clear and you know what it's going to do. But to somebody who doesn't do much R programming, that's sort of an opaque kind of way of coding things, because they might think, well, that looks like a matrix multiplication, or they might not realize that this is being done by columns, and it does sort of hide what's going on, and is something that might lead to more bugs because you might not remember that this is being done by columns versus rows and that sort of thing. Okay, comments or questions? Yeah, Tian.
How does the transpose code compare with percent?
That's a good question. I mean, when we're doing the matrix multiplication, that's going to be, if the matrices are all n by n, that's going to be order n cubed. We'll see that when we get to talking about linear algebra. If we're just doing the transpose, we could think about how many calculations get done and how many things have to get transferred. And there are only n squared elements in the matrix, so that's presumably something like an n squared calculation. So I would expect that the transposing is quite a bit faster than doing the matrix multiplication. We could try and work through that in more gory detail, but I think that's probably the way one would think about that. Other questions? Okay. So I just have a little bit here about just using apply here. I actually have that more or less that trick here about doing the column means or working with transposes. I think I want to. There's a sort of nice example of this in the demo code that I think I won't take the time to go over. But if this is something that interests you, you might take a look at that. It's because it's kind of cool, which is this rm rows 1, rm rows 2, rm rows 3 in the demo code file is basically trying to omit. Suppose that you get a matrix, and it's a big matrix, and you want to remove all of the rows that have any missing values, any NAs in them. So you could do something like basically look through each row and see if there are any NAs in there, and then remove those rows. That's basically what the second one is doing. But as we've already talked about, doing things in a row-wise fashion is often somewhat slower because of the fact that that's not how R is storing stuff. So there's sort of a cool trick for doing it in a column-wise fashion that basically takes each column and says which of these are NAs and basically is doing sort of a column-wise operation of ORs, Boolean calculations, to see if there are NAs in each of the elements, each of the rows that correspond to this column that you move along. So if you're interested in that, you could look at the details of that. So that's another example of this. So let's go back to, okay, so if we go back to the notes, a little bit about matrix algebra, linear algebra. I just want to make the point again that we can often do things in basically doing mathematical or matrix algebra operations. So an example of this would be that if we had a matrix and we wanted to do take the sum of each row, we could use row sums, which is quite fast and actually is going to be faster than what I'm going to say here. But we can also do that as a matrix algebra operation by taking a vector of 1s and multiplying that vector of 1s by each row of the matrix, and that will also do the summation. So you might think that if R is optimized to do pretty fast matrix algebra, you might think that that would actually be the fastest thing. It is fairly quick, but it turns out not to be quite as fast as doing row sums. So here's an example of finding the mean of each row in a matrix in 3 different ways. Here's using apply. In this particular case, that takes about 0.07 seconds. If I do it as matrix vector multiplication, it's about 5 times faster than that. And if I do it as row sums, it's maybe twice as fast as that even. So just again to show that there are oftentimes for a given calculation, there are lots of different ways to implement that calculation, and sometimes it matters how, sometimes things are substantially faster and sometimes they're, sort of moderately faster. Okay, let's see where I am here. All right, let's talk about a couple more examples where we can think about implementing stuff in a couple different ways. So the first one is, suppose I have two matrices, and I want to, or no, sorry, not two matrices. Suppose I have a single matrix. Suppose I want to take the difference between each of the successive columns of this matrix. So I want to take the second column of the matrix minus the first column, the third column minus the second column, fourth column minus the third column, and so on and so forth. So we can think about how we would want to, so we're basically doing sort of a lag operation of the sort of thing you might need to do if you're working with time series or something like that, except we're doing it on the columns. Okay, so if I did want to do that lag operation, why don't you take 30 seconds or so. I think the answer might be in the demo code, so if you want, you can cheat. But take 30 seconds or so and think about one or maybe two ways that you might be able to carry out this differencing operation, and see what you can come up with, and then we'll think about assessing which of those might be faster or slower. And one way is that there is a way to do it as sort of a matrix algebra operation. The other thing I'll comment here is often, I don't know if this works for everybody because people's brains work differently, but I tend to think about matrix calculations in sort of a visual way. So oftentimes it helps for me to just make a picture of the matrix like that, and then think about sort of manipulating it in a spatial sense. That might not be something that helps everybody, but that's one technique that I use. Okay, so what are some strategies that we could use for taking these successive differences of columns? All right, what's the obvious one? Okay, we could just do a for loop. That would be sort of the obvious thing to do, right? So, and I think I listed it up there. So we could think about doing a for loop. If we're doing a for loop on columns, we might think that would be better than it could be, because we are working with the columns. So that's one thing to consider. All right, so I suggested we could do it as a matrix algebra operation. Anybody have any ideas, either what I'm thinking of, or there might be other ways to think of this as a matrix algebra calculation? Michelle?
I was thinking you could create a matrix B that's just a subset of matrix A, and then just do subtraction.
Okay. So one possibility is you could somehow do a subtraction of some matrix A times minus some new matrix. We'll call it new A. Okay. So what were you thinking that these matrices would look like?
Well, I think A, okay, so A would just be the same, but the new matrix would be, like maybe the first column is just zeros,
Mm-hmm.
and then the next set of columns is A column 2 through the end.
Okay, so we need to sort of monkey with the columns. So that would be one way to do it. I would suggest that a slightly better way to do it would just be to remove columns rather than zeroing out columns. So if we want to do this matrix minus its sort of previous columns, we need the last column up through the second column, right? So we need something like A of 2 through n minus A of 1 through n minus 1, something like that. So that actually would work pretty well. Anybody see another way to do this? Okay, you could also do this as A of minus 1. and A of minus n. So this is a pretty slick solution because it's just going to involve very basic R operations and just very basic mathematical manipulation. Anybody seeing what anybody see how you could do this as a matrix multiplication? Hello?
If you have a matrix with you start by 1 and minus 1,
Okay.
and the rest is 0.
So if we want to contrast the first two columns of this matrix, I need to do it as minus 1, 1, right? And then zeros. So when I multiply this through by this matrix, it's just going to do minus 1 times this column plus this column. So that'll do that contrast. And then next?
0.
Okay, 0, minus 1, 1, 0. And you can continue in that fashion. So if you constructed this matrix, and there should be a way to construct this matrix fairly quickly because it's a pretty patterned, systematic kind of matrix, so you should be able to use ref or seek or something like that. We could do it that way. Anybody have any suspicion in advance of whether this is going to be faster than if we did it with this thing that I've partially erased of doing this direct subtraction of the matrices? Yeah.
It's all good working with sparse matrices.
Okay, so this matrix over here that has a lot of zeros in it, we'll talk about that when we get to linear algebra, is a sparse matrix. If we actually went through and did all the calculations where we did a lot of multiplications by 0, that would take a lot of time. And if these were big matrices, I've already said matrix multiplication can be fairly slow if they're big matrices because it's order. Say if these were n by n, it's order of n cubed. So we're wasting a lot of time in multiplying zeros by numbers because we don't need to multiply 0 by a number to know that it's going to be 0. We don't need to know what that number is before we do the multiplication. So if we could store this as a sparse matrix, which we'll talk about what that means in a few weeks, and do the multiplication, it might be fairly efficient. But if we didn't, then your suspicion, I think, would be true that the implication of what you're saying is that if this is not stored as a sparse matrix, then it might be fairly inefficient to do it this way because we're doing a bunch of multiplications that we don't need to do. Whereas this subtraction is really only doing the only doing the arithmetic operations that it needs to do, just doing the direct subtractions and not all these extra multiplications.
So
Yeah,
the
Daniel.
RBO sparse matrix works well with all the ordinary matrices.
Yeah, I think the one of the packages is matrix with a capital M, and I think that has various sparse formats that will work both with, they'll be able to do operations that combine sparse and non-sparse matrices fairly effectively. Okay, so I think this is sort of a nice illustration that if you're thinking about, if you decide that doing this lagged columns was really one of the bottlenecks in your code, and you decide your code wasn't running fast enough. Even if you decide it's the bottleneck, if your code runs in a second or 10 seconds and you only need to do it a couple times, you might not care. But if you decide that you do want to try and make things more efficient, and you decide that doing the column lags were the slow thing to do, the way that I usually proceed is I sit down and say, okay, here's this calculation. Let me sort of brainstorm about different ways that I might go about doing it. And we've already seen some examples where we've seen 2 or 3 different ways of doing the same calculation. Sometimes I'll have some intuition or already know because I've already tried this in the past about which is going to be faster, but sometimes I just need to go ahead and just try it out with benchmark or system.time and actually work through it. Okay, so let's stop there. We'll finish up with a little bit more on efficiency on Monday, and then we'll move on to whatever the next section is. Remember that you have some reading to do for section on Monday.
Question.
Yep, hold on one sec.